Muito bem. Now we are going to talk about connections, more connections, but a different type of connection. Professor Drude de Lacerda has a extremely large experience in this type of system, the interface between coast and oceans, and all things behind it. So not only biological, but also physical and environmental aspects related to this type of connection. And he is going to talk about these kind of things with you. So I introduce you Professor Luiz Drude de Lacerda. He is going to introduce himself, his background, and then I will leave you with him. Okay? Drude. Obrigado. Você quer projetar com o negocinho ou você quer sentar?
Não, eu projeto lá do computador. É só botar aí.
Tá, ele já vai
Tá. Well, good afternoon, and thank you for inviting me to this course. It's very nice to teach, because it's 3 years from now that I'm not teaching. I'm working on science management, so out of classes. So please allow me a certain difficulty in teaching. But I worked with the continental ocean interface for quite a long time. My background was formerly biology, but I worked for 20 years in a chemical institute, and then moved to a geological institute, and now in an oceanographic institute. And I think you're going to understand why. I mean, I work with biogeochemistry of the coastal zone, and you have to know a lot of disciplines to eventually understand what is going on. More? Better? Yeah, I'll try to keep it up. Yeah. The thing, yesterday, when I arrived here, people were talking about governance. Today, yesterday afternoon, and maybe during the whole week, they're going to talk about governance. I'm not going to talk about governance. I'm going basically to talk about the scientific basis you need to do good governance. And then after the break, I'm going to use the mangroves of Latin America and the Caribbean as an example of the bad use of science to make bad governance. And this is, in fact, bad may be not the right adjective. It's just, we've been discussing yesterday that science goes like that and governance goes like that. So it goes up and down, goes up and down. So it takes too long to reach. But this is a very significant problem of environmental governance, that when it eventually becomes a law or directive, changes are no longer the same. And we're going to see that in the second part of the conference on the specific aspects of the mangroves, for instance. Tá no outro lado? Cadê? It's why it's called personal computer. I know where I do this in my computer, but not in the others. No, it's all right. You can. You see, the coastal zone is very complex, and most of the information that is being generated in the past 3 or 4 decades, it's adding more and more complexity to the knowledge of the coastal zone. If we go back maybe 20 years ago, 25 years ago, normally this is how people face the coastal zone response to environmental changes. You normally take in consideration a unidirectional flow from the continent to the ocean, basically. That take into consideration the quantity of this flow, which depends on basin properties. So if you go to the papers of the 90s or the 80s, they are just flux measurements. And very, very rarely they talk about the variability or the intrinsic variability of these fluxes. Obviously, even though you have a high complexity, when you start studying the interaction between the major compartments, atmosphere, soil, river, this complexity already existed by them. But if you go nowadays to understand the response to the at the continent-ocean interface, things are a little bit more complicated. The first, and maybe one of the most important insights of the present century, is adding the ocean forcing as an important component of the coastal response. So you no longer have a unidirectional flow, that the basin controls all the flow. Nowadays, you know that the ocean forcing, mostly due to climate change, are a very important driver of the response of the coastal zone. We're going to see some examples. This is a very important thing. The second important thing is that human activities today are dominant in terms of source of material to any coastal zone in the globe, either directly by input of different substances directly in the coastal zone, either changing the behavior of the coastal zone. If you think, Antarctica, Greenland, you know, well, they are clean from anthropogenic influence, direct anthropogenic influence. But flow of melting ice, both in Greenland or in Antarctica, is potentialized by global change, and this is affecting the response in the coastal zone. One thing when you talk about governance is how we're going to include all this complexity in a framework that will end up in a proper legislation. To my view, this today is not done anywhere in the world because of our incapacity of including the complexity of the coastal zone response in our legislation. We're going to see also some examples. The major characteristics of the interface are basically what has ever been: transport of mass, energy, including nutrients, water, sediments, from the continent to the ocean. Yeah. Obviously, this still exists, except that today we know that this is not the only factor affecting the response of the coastal zone. Also, and this is something that's I remember in 1988, I read the first ever paper published showing the influence of the continent in the deep ocean. Before that, people didn't think. I mean, those compartments are completely segregated. The continents may affect the shelf, the continental shelf, but not the deep ocean. Today we know that even the deep ocean can be and is affected by what's going on in the continent. Another characteristic is that this process, they occur both directions, from the continent to the ocean and from the ocean to the continent. And this will be highly dependent, mostly on climate. So if you go to places like northeastern Brazil or some parts of Western Africa or some parts of Australia, where rainfall is very small, you are nearly under semi-arid climate, frequently the ocean forcing is more important as an influence to the coastal process than the continental materials transported to the coast. We're going to see that. On the other hand, if you have a humid climate like you have in the Orinoco, the Amazon, even the Congo, no problem. The continent keeps on being the major driver of the response of the coastal zone on the biogeochemical process. And obviously, the third thing is that not only natural vectors, but also drivers of anthropogenic origin are today even more important than the natural drivers. In fact, when you think about natural drivers, like rainfall. Even the natural drivers today has a very strong anthropogenic signature, meaning that you probably don't have in the world, in Earth today, any natural, 100% natural process. All of them are affected in a way or another by the anthropogenic activities. So talking about natural drivers is maybe a fallacy in the end. In the Holocene, in the beginning of the Holocene till maybe the last century, the beginning of the last century, maybe earlier, beginning of the 18th century, natural drivers were the major controllers of the process occurring in the continent-ocean interface. Geotectonics, for instance, dominates the sea level maybe for the last 2,000 or to 10,000 years. Nowadays, global warming in certain areas are more important than geotectonics, for instance. Wind, earthquakes, hurricanes, tsunamis. Obviously, the human activity cannot affect a hurricane, but can affect the frequency of occurrence of hurricanes. So you don't need to change the driver, but you can change frequency of this driver, intensity of this driver. And obviously, the response in the coastal zone will be different. Coastal vegetation type, we're going to see that it's probably one of the most significant drivers of the biogeochemistry of the interface. Major anthropogenic drivers, you all know, people talk about it every day, which is wastewater, agriculture, pollution, emission. And these are the obvious things that happened since industrialization and urbanization. But there are others that are not so obvious, like damming of a river, for instance. Damming of a river not only make the fluvial flow regular, but blocks sediments. And once you do that, at the coastline, you break the equilibrium between erosion and sedimentation. So you change anything. And this is quite curious, because most of these dams are very far from the coast, and normally not taken into consideration when you do, for instance, coastal zone management plans. So you do a coastal zone management plan for the coastal area of the São Francisco River in Brazil, for instance. And you don't take in consideration the operation of the Xingó Reservoir, which is the largest in Latin America. And obviously, nothing works because of that. So to do a good evaluation of coastal zone management, you have to include what's going on in the basin, and depending on the basin, very far inland. Same thing with global climate change. It's very difficult to exactly characterize the major impacts of climate change on the many facets of the coastal zone, because it's not only sea level rise. For instance, we were very efficient, and yesterday Professor Allen talked about that, in controlling pollution emission by industry, for instance. I mean, there are many international conventions, many laws at municipal, state, federal levels that control more efficiently the emissions of pollutants. But now with global change, a large amount of pollutants that has been deposited in the coastal region as a legacy of these irresponsible years of technological development without caring about the environment is being remobilized by global changes, global climate change. We're going to see an example here which is happening in extreme parts of the world, in polar regions, in semi-arid environments, where climate change is remobilizing a legacy of pollutants deposits in the last 200 years. So the effect of the two classes of drivers together is probably the most complicated aspect of interpreting what they are going to do in the coastal zone. Because one can affect each other. For instance, in tropical coastal areas dominated by mangrove, anoxic environments are dominant. Therefore, all the metabolism of the biota is adapted to anaerobic conditions. One of the first things that global change may cause is sea level rise. In terms of biogeochemistry, just meaning putting oxygen into an anoxic sedimentary environment, therefore releasing everything that is stable under anoxic conditions. So how this will react is very difficult. We are already measuring the impact of that, for instance, in exposure of human populations to pollutants. We're going to show some of these results later. So it's very difficult to understand how this process interacts. And normally they are very site-specific because they depend on those properties I showed in the first slide. Basing properties, other anthropogenic activities interacting in the area. Where in the ocean you're talking about, because ocean forcing is also not even distribution along the globe. If you are in the Arctic, it's one thing. If you are in the tropics, it's another thing. Even in the tropics, humid tropics and dry tropics behave completely different. So it's a very site-specific situation, very difficult to appraise. And our knowledge of that is still very, very small. Major effects of these anthropogenic drivers are basically accelerating biogeochemical process. I mean, when you have effluents from agriculture or from wastewater, what you do is accelerating primary productivity. And then when you do that, you imbalance food webs. Certain species are no longer those better adapted to high nutrient content of the waters and are substituted by others, and therefore you start making a cascade effect, substituting everything. So first thing, they accelerate the cycles. All water, sediment, nutrients, pollutants. They change the quality of the material that is available in the environment. From the extremes of absolutely shallow compounds, like compounds from the nuclear age, which never existed before. Lots of radionuclides are artificial. Organics made by human technology, which is also artificial, but even natural compounds that have their chemical speciation changed due to an anthropogenic driver. For instance, changing from an anoxic state to an anoxic state. Lots of substances precipitate under anoxic condition or oxic conditions, and vice versa. I remember some years ago when they first made the first plans of cleaning the Guanabara Bay in Rio de Janeiro, which is a sewage deposit, no oxygen at all. And they asked us to discuss the problem and said, well, you have to make some evaluation of the bad aspects of the cleaning. There's no possible, cleaning the bay is fantastic. Yeah, it's fantastic. But when you clean, you're going to dredge, you're going to put a lot of oxygen in a system that is accumulating pollutants under anoxic conditions for decades. When you do that, you're going to release an incredible amount of pollutants. For instance, that time, if you measure trace metals in fish in the Guanabara Bay, it's much lower than in any paradise in the Caribbean. Although in the sediments, you have pollutants that you could be mining and produce jewelry with that, the amount. But it's not available for biological uptake because of the anoxic condition. But once you put oxygen in it through dredging, for instance, then you release all this matter for biological uptake. Then this is one aspect very important from anthropogenic driver. They are able to change the biogeochemistry of the environment, the major biogeochemical parameters of the environment, like oxygenation, temperature, pH, and so on. Then it changed the species of elements and therefore their bioavailability and toxicity. Also, fluvial discharge in the ocean today are basically controlled by us. There are very few rivers in the world that is still flowing to the ocean like it did some 1,000 years ago. In Brazil, for instance, if you go to where I work in northeast Brazil, a semi-arid climate, you have 95% of all the natural runoff artificially controlled. So what you're talking about? You're talking about a coastal zone that is no longer natural. Even if you have beautiful seaside and beautiful plants and animals and dolphins and everything, it looks like a natural thing, but it's not. Because the major controller of what's happening there is controlled by human activity. And there's, people from China witnessed this with the large dams being built there and everywhere in the world. In fact, most bases in the world today are a human thing, no longer natural. One way of looking at this is not a complete thing. I mean, I've seen some posters there on this DPS-RE analysis, which is a very good analysis and serves for our purpose here. Most of the drivers from humans are basically agriculture, including aquaculture and husbandry, urbanization, industrialization, dams, and global climate change. And the major pressures are changing the biogeochemical cycles, increasing loads of sediments or decreasing loads of sediments, increasing or increasing water availability, contaminants, and decreasing the permeability of surfaces. This is very clear when you work like I work in the Northeast, when you have only maybe 2 or 3 months of rain and 8 months of dryness, and the runoff that comes from agriculture areas and the runoff that comes from natural vegetation areas. Yeah? I mean, runoff from agriculture areas are truly rivers because of soil impermeabilization. Dams, basically altering the balance of sediments in the coast, but not only that, because since most of the sediments are kept inside the dam, you not only break the equilibrium, but you also make some elements like silica deficient. So you directly affect primary productivity. And those things are not taken into consideration. Never. Regularization of the flux. This is something that today in Europe, in the States, there are large movements to blow up the dams to give the rivers back to their normally seasonal variation. And this is a very important thing. And we're going to show some examples that's happening in the area we are working, which is similar to many areas of the world. Global climate change, basically sea level rise and rainfall regime. Therefore, it impacts directly on the continental flow to the ocean. They impact sedimentation, eutrophication. We're going to see many of these examples. And another thing, although these tables are very nice to have a quick view of the environmental impact from human activities, they fail to go a little bit deeper. Eutrophication can be completely different and is completely different from agriculture and aquaculture. We're going to see some interesting examples of that. Because although the process is the same, the drivers for this process, which is basically carbon, they are from different origin. If you are talking about effluents from aquaculture or effluents from agriculture. This is another interesting thing. One of the major impacts that you normally, it's something that you have, even myself, I took some time to actually understand this. When you talk about the carbon cycle, the continental runoff of carbon to the ocean is transporting a carbon that can be, and normally is, thousands of years old. Because they came from a plant, but stayed in the soil for different periods of time, and decayed, and was degraded. And when it eventually reached the sea, it's very difficult to immediately produce any kind of changes, because they are very hard to be oxidized. While in the sea, no, the ocean is accustomed to a carbon that is very easily oxidizable, very new. And this may create very important and significant information for management proposals. So also the process, they have the same name, they are the same process, but they can be completely different depending on the anthropogenic driver that caused them. Eutrophication as an example. Let's look at those major drivers. This, someone has already put pictures like that. This is a very nice paper that is available. I think I posted to you. It's a review of the continental runoff to the oceans all over the globe. And mostly what we have today is that most rivers in the higher latitudes are increasing their flows to the ocean due to mostly ice melting, glacier melting, and permafrost melting. While in the tropics, specifically on the more drier coast, but also in tropical humid coast, the continental flux is decreasing. So you are increasing the continental contribution to the ocean in the higher latitudes and decreasing in the lower latitudes. This is the major conclusion of this paper. Although, this is very interesting because these guys, they reviewed the information for nearly 1,000 basins. But they could only use less than 70. Because most of the others, the gorges, are located too far from the coast. So what is measured there is not what actually goes into the sea. But it's something that you don't know. I don't know what that measure means. It measures the flow from a part of the basin, but if it will reach the sea or not, we don't know. So there's only 70 out of 1,000 basins that you have monitoring at least close to the coastal zone. And then you can actually see what's going on to the ocean. But there's a very important thing, because if you think that the source of most materials to the oceans are either from the atmosphere or from the continents, then you can have a nice picture. I can easily say that in the Arctic, you are increasing the continental flux to the ocean. So I can expect increasing productivity because more nutrients are arriving there. I can expect increasing pollution because more pollutants are going there. I mean, they receive atmospheric deposition of many pollutants for many years that is now being melted. And on the other hand, I would expect oligotrophy in the lower latitudes because the major source of nutrients to the tropical ocean are the continents. If you go just a little bit out of the continental shelf, there's no productivity. You don't have any source, significant internal source of nutrients in the lower latitudes. So I could say, well, therefore, transport of nutrients is decreasing, but also the transport of pollutants. But it's not like that, really. And you're going to see some examples where things are a little bit more complicated than what this picture shows. Also, there is many different geomorphological settings that will create different response of the coastal zone. This is independent of anthropogenic or natural drivers. This is an example of Brazil that you can characterize many systems by their geomorphology. That will be accumulating system, like most of the bays and coastal lagoons that you have anywhere in the world. Well, in many others, you have a flux, a permanent flux of water to the ocean. And this, when the Portuguese arrived here, was probably exactly like that. What happened today is that anthropogenic actions upon these systems are changing a little bit. For instance, most of these rivers to the north, except for the Amazon, they occur under semi-arid conditions. And they normally depend on a very seasonal flux of water and material. During 2 or 3 months, you had a lot of water flowing into the ocean and plumes formation. And during the dry season, the ocean comes up. When you put a dam on it, then you reverse. So most of these exporter systems, like the São Francisco River, the Jaguaribe River where I work, are today no longer exporting anything. They are importing things from the ocean because of anthropogenic intervention in the basin, in this case, dams, damming of the river. So some of them are changing. Others, like Sepetiba Bay, for instance, we're going to see some examples in Rio, also due to anthropogenic activities, in this case dredging, become frequently exporters of material. So a lot of material that is deposited naturally in these areas frequently are exported to the ocean due to dredging, for instance. So even the geomorphological framework, which would be something quite absolute, is no longer absolute. Even those can be changed by human intervention. Normally the exporter system, like some of these rivers that I show, they have a very interesting characteristic which you can see, which is forming river plumes during the most of the year in case of humid climate, and seasonal and semi-arid conditions. Up here and here is the Jaguaribe River. This ocean area is the smallest primary productivity ever recorded in any place in the world. There's nothing there. So all the productivity depends on this. Yeah. So rarely during the rainy season, this plume is formed in the ocean and brings a lot of silica, a lot of nutrients to sustain the primary productivity. And then you have a very seasonal patterns of productivity. When you dump this river, you cut the plume. So you no longer have the plume. Wow, it's not interesting. But not only you don't have the plume, but now the ocean becomes dominant. And you're going to see what happened. Not only the plume disappear, but the ocean goes into the continent. And you have oceanic condition inside the continent. Whereas these systems that accumulate material like bays and lagoons, they normally create large depositional areas able to sediment a lot of material. In fact, 90% of our legacy of irresponsible pollution during the 70s and 60s is now buried in coastal sediment here. So anything that will provoke erosion or anything will make this legacy available again. And this is a complication in terms of management or governance, because in the 60s, if an industry flows a lot of pollutants in an area like Sepetiba Bay, like it did, there was a cadmium smelter here that was simply closed because of that. Yeah, the fines were so high that the industry could not thrive and was closed. But nowadays, when there are dredgings or when there are cold fronts, you remobilize metals, the same cadmium that contaminates the biological resource, exactly like it was 40 years ago. One major difference: there's no factory to close. There's no one to pay for the contaminated fish. There's no fine to apply. There's no one to process. And this is probably one of the major problems of governance today. How are we going to do this? I mean, it's the society that has to pay for something that I can say, I have nothing to do with that. But no one has nothing to do with that today. So this is what happened in a typical retention system. I mean, this is in southeastern Brazil, but it's valid for everywhere. One important thing, you see that nearly 90% of everything that comes from the continent stays in these filters. In fact, in a global scale, about 50% of everything that comes from the continent stays in this estuarine and the deltaic sediments. About 30% goes into the shelf, and maybe 10% of it can go into the deep ocean. But everything is kept there. But it's not only a question of quantity, because you change. For instance, if you say carbon, for instance, there is dissolved organic carbon and particulate organic carbon. Most of the particulate organic carbon is retained inside the bay, in the inner parts of the bay. Some of the dissolved carbon is already also retained here. But then we go out, the nutrients that came from the decaying of this organic matter start fueling productivity. So you have, again, another rise of carbon dissolved carbon, and even particulate carbon as phytoplankton. But again, there is a difference. Here, we're talking about an old terrestrial carbon, very difficult to be oxidized. Here is a new carbon, fueled by nutrients, but the carbon is from the atmosphere by marine plants. So it's a very new oxidizable form of carbon. And then this is important to understand some difference in eutrophication capacity. In exporter systems, and this, as I said, is something at least 40 years old, which is quite new in terms of science, which is the capacity of these systems affect even the deep ocean. There's a distribution of mercury in the southeastern coast of Brazil in an area of sugarcane production, which up to 1986, they used mercury as a fungicide in the sugarcane agriculture. Then it was forbidden. But by that time, they still use a lot of mercury, and you can follow this mercury up to very deep areas in the continental shelf. In fact, this station at 30 kilometers, about 2,000 meters deep, and you can measure it there. There's not in there, but you can see it in a core, the increase in mercury concentration from the beginning of the 70s, when they start using mercury in the sugarcane plantation, up to the 90s. And then it dropped again, because it stopped using. Yeah? You can see in this graph below how this behaving relative to aluminum. Aluminum is a continental material. The sea doesn't produce aluminum, so it's a very good tracer of continental material to the ocean. Not only because it comes from the continent, but it's abundant and doesn't change. I mean, aluminum is a quite resistant metal. But that's agriculture. I'm talking about agriculture as a driver. This is the impact of irrigated agriculture that produce fruits in northeastern Brazil. Again, you can follow aluminum going down to very deep areas out of the continental shelf. So those activities, they are not restrained in the coastline, least in the continental platform. You can really trace them down to the deep ocean. And this is a concept which is not very easy to follow. And once this is happening, then the process that are typical of marine continental shelf starts also acting upon these substances. So first, as a biologist, the first time I heard a geologist talking about erosion of continental shelf sediments. He said, erosion of continental shelf sediments? You know, erosion is a river or water passing through soil or whatever. But it happens in the continental shelf. I mean, there is a movement of finer particles to the deep areas, exactly like you have in the river. So, although it's very difficult for us to think about a continental shelf as a river, but it is a river. River very, depending on the area you are in the globe, in a very steep area. And steep areas provoke transport of material, differential transport of material. And these things start, obviously, what you can see is that most of the metals are accumulating in the slope because they are associated with fine particles. Fine particles has a much larger area. Therefore, they will follow the erosion of large particles, like you see there. You can see the accumulation of clays in the deep areas. Therefore, you're going to accumulate metals in the deep areas. And this is a very interesting thing when you talk about governance. Brazil produces a lot of, nearly the totality of its oil from offshore facilities. And there is a very large legislation regulating this activity. And one of them is the emission of pollutants. And this is very interesting. Because whenever any kind of pollutant that comes from one of these offshore platforms, they are located here, and the concentrations here, where they occur, is very low. So people interpret that they emit very small amounts of metals. But this may not be true. Simply that the metals emitted here are accumulating here and not there. And our present-day legislation is not able to include these aspects. So the conclusion from an environmental report will be these platforms are not contributing with any metals at all. I can post a book we wrote on this constraints of the monitoring of offshore oil facilities. And one of the major things is that you cannot see any increase in any kind of pollutants, except if you follow the natural process, then you're going to see. But then how are we going to say that that specific mercury or lead deposit there came from the platform? That's complicated. There is also a temporary component of the variability of the continental flux in the shelf and in the deep ocean that depends on the climate, basically. So this is the Paraíba do Sul in Rio de Janeiro, which is a humid climate. You have a difference in winter and summer. You can see here the salinity silicio. Silicio also comes only from the continent. That there is a difference between the two lines from winter to summer, but it is very small, meaning that you normally have throughout the year an estuarine-like distribution, yeah, from the continent to the sea. But if you go to a place under semi-arid climate, like Jaguaribe in Ceará State, then remember the colors. All green balls are fluvial water, meaning not that collected in the river, but fluvial water, fresh water. Yeah? And then here is estuarine water, plume, and the shelf waters. During the rainy season, river waters are exactly where they have to be, in the river. Low salinity waters are in the river, while high salinity waters are out in the continental shelf. So exactly like you have in the humid climate, a estuarine gradient, where less salinity water is inside the river and is increasing salinity as you approach the open ocean. But if you go now to the dry season, then you have a shift, mostly where? In the interface. You see this estuarine yellow balls where they are during the rainy season? They are close to the freshwater end member, low salinity. But during the dry season, they start migrating into the sea. So it's like in dry season, in semi-arid climate, the estuary advances into the continental shelf because the ocean is coming on. Oh. Again, this is salinity uranium salinity, which is a very good uranium coming from the ocean. So it's a very good tracer of water masses. Again, rainy season, dry season. During the rainy season, perfect. The freshwater samples are in the freshwater, inside the rivers. The estuarines are in the estuary, the coast is in the coast, and da. When you go to the dry season, then things change completely, because this is river samples with 25% parts per thousand salinity. All the estuary and all the plume, in fact, is ocean water. So what you have is the ocean advancing over the continent, and you think you are sampling the river, and you are sampling actually ocean water. And most important, they block the continental flow. So during this period, the continental flow is retained in the estuarine area. They don't migrate into the ocean because the ocean forcing is too large. It acts like a wall blocking the continental flux. This increases the residence time of this material in the estuarine zone. And this is very important because it's where things happen. So this material has much longer to react, to change, mostly chemical changes, important changes, and depending on the estuary, this has a direct result on bioavailability and toxicology in case of pollutants. Well, this is another example of an induced seasonality in the Yangtze River. This is after the blocking of the dams. And you see clearly the ocean migrating into the continent during the dry season. This is occurring everywhere in the world because of damming, except with the large rivers without a dam, like the Amazon or the Orinoco or the Congo. But most of the other rivers are experiencing this importation of the ocean. Here's a comparison of two rivers in Brazil, one on a humid climate, which is in South Bahia, and the other one I'm going to show in a semi-arid area. And this is very interesting because it shows also the velocity of the fluxes, yeah, and the salinity. So when you have the ebb waters, the largest flows are from the river to the ocean, as expected. But if you go to a semi-arid, then it's just the opposite. The tidal water is much more stronger than the continental water going out of the ocean. This is the blocking effect I'm talking about. Yeah? Here, there's no blockage because the largest velocities and fluxes occur during the low tide, taking the continental material to the ocean. But if you go here, it's different, just the other way around. The flooding is much stronger, higher volume and velocity than the continental flow. So there's a kind of a wall. It's literally a wall. Materials cannot pass over this wall to the continental shelf. So it accumulates in the estuary. Not only sediments, but also carbon, nutrients, pollutants. Yeah? And this has a very important aspect. When we think about the major problem is what happens to those crazy deposits of irresponsible environmental activities we did in the 70s and the 60s. Once in the continental shelf, then you're going to depend mostly, as I showed before, on the characteristics of the continental shelf. And then I'm not going into it because it depends on the largest, the deepest, and all oceanographic feathers of the continental shelf. Most of the interface between the continent and the ocean, because of this abundant continental material, is normally of very high productivity. And all over the world, these areas are dominated by quite characteristic communities. In the tropics and subtropics, mangroves, in higher latitudes, salt marshes, mostly. Then you're going to polar latitudes that there's nothing there. And most of the world, between 20 degrees north and south, are occupied by mangroves. Salt marshes does the same thing. The only difference from what I'm going to talk about mangroves is that due to the very low temperature and being grass that dies yearly, it occurs in a seasonal basis. In mangroves, it occurs all over the year. Someone already told that those are probably the most efficient pump of converting CO2 into organic carbon per area, all over the globe. You're going to see some results at the global level that is quite impressive. And this kind of vegetation, in most parts of the world, loving what we are doing with climate. They are expanding in many areas of the world because of global warming. The major impacts of this kind of vegetation, and as I said, salt marsh does the same thing, except that it does only parts of the year. So the things are a little bit balanced because there is erosion during the dry season. But mangroves works like that throughout the year. So their signature is much larger. First thing, they increase the sedimentation rates. Everyone that saw a mangrove, maybe all of you have seen a mangrove. It's even difficult for us to cross a mangrove. So you can imagine a poor particle being transported by the river crossing a mangrove ecosystem. So the first thing, you increase the deposition of fine sediments. And what is important, fine sediments are the only part of the sediments, with few exceptions, that can be transported from the continent to the ocean, because all the large sediments are staged in the continental area, sands, for instance. And small particles, fine sediments, has a huge surface area. So all nutrients like phosphate, nitrate, all pollutants are transported mostly associated with fine particles. So wherever you have an increase in sedimentation of fine particles, you're going to have an increase in sedimentation of pollutants, nutrients, and whatever, transported by these particles. So that's a very important thing. Meaning that if you analyze a mangrove soil anywhere in the world, it will be richer in carbon, nutrients, and pollutants than any other sediment close by, not covered by mangroves. Well, since it produces a lot of carbon, I mean, mangroves are more efficient in primary productivity than sugar cane. Even our Brazilian sugar cane, which is an artificial thing that we created in Embrapa, which is very efficient to transform CO2 in organic carbon. But mangroves, even much more than sugar cane. And one thing that is very important, mangroves are a terrestrial vegetation form. They are not marine plants. They are terrestrial plants, about 70 million years old, so they are there for quite a long time. So they are very good plants to survive. Very few plants have this age. And they are terrestrial. So all this organic carbon that they produce is a terrestrial carbon, meaning cellulose and lignin mostly. There's not, with except with manatee, a single sea animal able to eat cellulose or lignin, except for the manatee. Or if someone creates an artificial cow that can go and live in the sea. Apart from that, there's no way. So this organic matter at the sea, it's very difficult to be decomposed. That's why over 60% of the organic matter produced in the mangrove is accumulated inside mangrove sediments and not exported anywhere. And what is exported accumulates in estuarine sediments or in deltaic sediments because they are very difficult to be utilized by the marine biota. So it accumulates a lot of organic matter, a very refractory organic matter, and the microorganisms are not able to oxidize this organic matter. So it uses the totality of the oxygen, and still there are lots of organic matter to be used. So they start using all the iron, all the nitrate, all the manganese, and the only thing that is left is sulfite. Sulfate is abundant. The energy that the bacteria get by using sulfate to oxidize organic matter is poor, but it's abundant, it's free. So in the end, after you consume oxygen, iron, manganese, nitrate, you have sulfate. So the whole metabolism of these mangroves are based on sulfate reduction, a dissimilatory sulfate reduction. The bacteria is not interested in the sulfur. It's interested in the energy to oxidize the organic matter. So a byproduct of this is sulfite. And sulfite precipitates all chalcophilic metals. In fact, they are chalcophilic because of that. It's a typical method for any second grade school of chemistry to quantify zinc, for instance, is mix it with sulfite and gravimetrically measure it. So if you put any dissolved metal in this environment, all of them, with few exceptions like chromium, manganese, that do not form a sulfite, will be deposited sulfite and accumulates under anaerobic condition. So as far as the anaerobic condition is maintained, these metals will be left forever. In fact, many countries are using mangroves to detoxify contaminated areas. I'm going to show an example in Guanabara Bay. There's lots of contamination. As far as the mangrove is kept there, if it's If you cut it to put a shrimp farm, then things change completely because you put oxygen. And you see, we're not talking about metal sulfides, the classical geological pyrite that you use for making jewelry. We're talking about a biological pyrite done by bacteria in less than 6 or 7 hours, which is a framboid. You're going to shoot some pictures. Beautiful, but very easy oxidizable. So this preserve also increase the preservation of organic matter. So it's a kind of a feedback. Large production of organic matter consumes the oxygen. Therefore, it turns into an aerobic metabolism, which is not able to oxidize the organic matter to 100%. So you keep on accumulating organic matter. But one thing is important. You not only accumulate the refractory organic matter, but since the sulfate reduction is not able to oxidize 100% of the organic matter, it produces a lot of dissolved organic compounds that is visually seen in any mangrove creek. Anyone that passes into the mangrove creek see that it looks like oil, but it's not oil. It's dissolved organic matter, which has a very high complexity capacity. So this is what normally happens in a typical mangrove ecosystem. I mean, everything is transported by particles, and they are deposited in the mangrove because in a system like that, you can hardly see anything going through. Once it's deposited, it changes from an oxidized environment to an anoxic environment. So the metals are released and reprecipitated as sulfides. Normally, they are transported by iron oxides and manganese oxides that obviously turn from 3 to 2 or 4 to 2 and release the metals which are further precipitated in sulfides. And this is fantastic. You can use this mechanism to clean areas. But don't mix with that. The process is that. I mean, it's basically dissimulatory reduction of sulfide into sulfate in sulfide, forming those beautiful crystals, which is framboid pyrites. They are really beautiful. At least I think they are beautiful. Maybe not. But one thing is that they are mostly, obviously, iron sulfide, because iron is the most abundant element. But any chalcophilic metal available in the area will co-precipitate. So it can be copper, platinum, gold, for instance, silver, lead, mercury. All the chalcophilic will co-precipitate with that. And will be very good, and this process is able of really cleaning the complete environment of trace elements, as far as it's kept like this. This is badly placed. It was before. Well, this I should have talked to this before. It's very good because we're going to pass to today's process. So what are the magnitude of this process today and how the anthropogenic drivers work on them? You have two different kinds of anthropogenic driver. One which is nowadays not as common that it was in the 70s, which is a direct emission of an exogenous substances. For instance, most of the industrial pollution of the 60s and the 70s. So you cause an alteration in the environment because you put a toxic substances or a substance that is not toxic but in too high amounts like nutrients and provoke eutrophication, things like that. And the other vector, which is more typical of our 21st century, which is vectors that interact between themselves. Effluents that wouldn't have any problem if there was no damming. Effluents that will have any problem if there's no climate change. Or if different sources are not linked in the same basin. So these are a little bit more difficult to cope with because they don't directly change the state of the environment. They act by changing different characteristics of the environment. Meaning that the whole Brazilian legislation, the famous CONAMA 457, do not apply to that because they work on limit. or maximum concentrations of elements or whatever. This is the first one. And the first one is very easy to control and has been controlled. This one, we still don't have a legislation. Meaning, what is the amount of mercury that I can allow to reach the Jaguaribe estuary without causing a problem? Then you can use this legislation, CONAMA, which is the National Environmental Council law for maximum concentration of pollutants and substances in the environment. For this first, you can use it. But here, no. Meaning that very small concentration, depending on the situation, can result in an enormous impact into the environment. I'll show one example in a very pristine area where people are presently threatened by a high exposure to mercury, in an area that there's no mercury pollution. Yeah? And no natural deposits of mercury, yeah? Except from atmospheric deposition. So this is what we have in the 60s and the 70s. Yeah? Point source of contamination all over the globe. And there's obviously, I think Professor yesterday talked about many accidents. And accidents, they are terrible, but they are very good because people see them. And then they can act upon them. Yes? Dioxin in India, mercury in Minamata, and many others. And then you immediately, the society immediately responded to them. But if you have a chronic problem, then it's much more difficult. So by that time, this resulted in a very strong environmental legislation throughout the world. The Brazilian legislation, for instance, is one of the most strongest regarding this type of sources. Industry, large urban areas without sewage, large harbors. But then, when you go in the northeast of Brazil, none of these things existed there in the 70s. There was no industry. There's no large urban settlements. There's no large harbor. There's no point source of contamination. However, and today it's still, when you think about Northeast, you think about beautiful beaches, lobsters, caipirinhas, and, walking naked on the beaches. It's a beautiful place. And if you look, and it is beautiful. I live there. It's fantastic. The water is clean, transparent, full of fish, lobster. But when you evaluate, and this is based on 19 estuaries in the Northeast, the semi-arid Northeast, where the least industrialized, the least urbanized area. And you evaluate the amount of substance going into the coastal area from the different sources, you already arrive to a conclusion that for nutrients, like nitrogen and phosphorus, over 80% of the total load is from anthropogenic sources. Well, this is not really a surprise because population increased there, but most of the cities has sewage treatment. However, the emissions are very high. But then when you go to elements like copper, which is typical from industry, mercury, then again the anthropogenic emissions are already much higher than the natural emissions. So from where these elements are coming? I mean, there's no factory producing copper, but they use copper in agriculture. There's no factory or mining of mercury, but agriculture use fish meal, oceanic fish meal, that has a lot of mercury. So there are lots of sources which are not classical sources of these elements, which nowadays are contributing much more than the natural sources, which are basically atmospheric deposition and soil runoff, to those estuaries. Other elements, fine, lead, cadmium, the natural sources are still the most relevant. What does it mean in terms of ecology of this region? It means that all the natural communities there evolved the past 10,000, 10 million years, depending on the type of ecosystem, under this emission of elements, both nutrients and contaminants. In certain of them, you are nearly doubling, multiplying by 10 this emission. But you don't see anyone dying. Well, nowadays there were some problems already occurring that you can see. But normally you can see. It's kind of a feeling. If I'm if I evolved with 10 kilograms per year of nitrogen, and then suddenly I have 100 kilograms of nitrogen, well, things probably will change. So it's quite probably that all the organisms today living there are not the same organisms living 200 years ago. Except that you don't know that, because maybe we have, well, historical records of jaguars, of monkeys, of large animals. But you don't have a phytoplankton, for instance. So I don't know if the species of phytoplankton today in the Jaguaribe estuary are natural or a result of this already larger anthropogenic scenario. And then, because of that, we're very worried about, well, what are the sources of these elements? And then we studied the emission factors of these activities. The first line is what we'd expected without the human presence, natural sources, basically atmospheric deposition and soil runoff. Even if they are, but atmospheric deposition brings mercury from Europe and the States, yes, but think that they are natural, that they are being diluting, fine. It's not, but fine, think they are natural. And then agriculture, husbandry, urban waste, solid waste, and shrimp aquaculture. And then, obviously, when we start doing this, we say, well, you know, sewage, it's terrible, the worst thing. But when you look about the emission factors, for instance, of copper in agriculture, it's much larger than any other emission factor. Because this kind of agriculture is basically fruit and use copper sulfide as a fungicide, a very efficient fungicide, which is not even toxic to the guy that is applying. So in terms of agrotoxic use, it's fantastic because you don't use those things that kill the people that are using it. Copper sulfide is cal da bordaleza, something that the Romans used. But the emission is very large. So we can explain why there's so much copper, since most of those basins has fruit culture. But then you say, well, solid waste obviously is an important problem of most of the elements. But look at simple aquaculture. You produce shrimps, and shrimps eat algae, eat aqua feeds. But when you see the emission factor from simple aquaculture of copper and of mercury, they're immensely high. In fact, aquaculture per area emits to the environment more mercury. This is shrimp aquaculture. So you use fish meal. It's from where the mercury comes. Bycatch in the ocean. Ocean species has a lot of mercury. And what you do when you make an aqua feed or fish meal, you just concentrate the mercury. So in the end, you have a very high concentration in the aqua feed. So the emission, and obviously the shrimp doesn't use the mercury, and it grows too fast even to incorporate the mercury. So all this mercury will end up in the feces and in ecdysis and eventually be released into the estuary. The only thing is that we are talking about only 300,000 or 400,000 hectares of farms. So the amount is very small, yet. But then we're going to see in the second presentation the disgrace that the new forest code of Brazil can result because of that. Yeah, because of not including what we already know about climate change and mangroves. They just released the salt plant behind the mangroves for development, mostly shrimp culture development. Then we are talking about 600,000 hectares. And with this emission factor, we can easily forecast an important contamination of mercury from shrimp culture. But then you're going to say, well, then easy. You know, find the guy there. You know, put him in jail. They are contamination. And they say, sorry, but I produce shrimps. I don't produce mercury. So what are we going to do? I mean, who is going to be blamed? No one. And there is another thing that is important to know. I mean, the natural inputs of all these substances are mostly associated with particulate matter. So very low bioavailability, and will be eventually deposited in the sorbine and the deltaic sediments. But then you go into all the anthropogenic sources. In fact, the first major characteristic of an anthropogenic sources is the diversity of chemical species it produces. Some of them that's not even possible to occur naturally in the environment. Yeah? And this is particularly important in terms of bioavailability. So we transform these emission factors into annual emissions of this substance. And this is an example of Fortaleza, where I live, in 1939, because since these activities are nearly the same in both times, except some treatment plants and things like that, you have to make some corrections. And this is Fortaleza in 2007. So annual contribution, examples of mercury, lead, and nitrogen. And all of them has increased at least one order of magnitude, at least, from sources that I'm not talking about lead mining, nor milk factory that produce a lot of nitrogen. This is basically urbanization. This is exactly the situation that you have today on the legacy of contamination of the 60s and the 70s. This is Sepetiba Bay. This is the smelting, the cadmium and zinc smelting factory. And this is the tailing deposits. And this has been closed in 1986 because of contamination problem. So the problem is no longer going there and obliging the owner of the factory to create a treatment for the effluents, or putting filter, or changing technology. There's no more owner. Yeah? So the state, as owner, just forget about the problem and left the effluents like that. So whenever it rains, the effluents go into the bay. Yeah? And worst, this is the sedimentation in the bay. As we showed, an importation of material results in large sedimentation. So most of the contamination today are below the surface of the sediments, depending on the sedimentation rate, 10, 20 centimeters. And in this area, the same government that would be responsible for this environmental passive decided to create a huge harbor there and start a frequent, nearly yearly basis dredging of these sediments. So suddenly they just start dredging the sediments, and there's no trace metal there. And then they start digging more, and then arriving the depths of high metal concentration. And this is not only large industry. You remember the Rio de Janeiro in 2007, the Pan American Games? And they have this the competition, ore competition in the lagoon inside the city. And they have to dredge that. The lagoon during the beginning of the last century up to 1950s received runoff from the city directly. Later in the 80s, they create a barrier that collects all the runoff from the city and divert it to a submarine outfall. And then you easily see the concentration of everything doing like this and then like this. Yeah? Till they make this barrier, everything goes into the lagoon and accumulates there. After that, all sediments came and nothing else, because everything from the effluents of houses, of hospitals, or everything goes out to the sea. And there's meaning maybe 25 centimeters of clean mud. But then they have to dredge the thing for the competitions. So by that time, there was a student of mine following what happens with the mercury there. And there was no mercury, because if you analyze the surface sediment, there was no mercury there. Because most of mercury going to there came from these facilities, and all go to the sewage system. And the sewage system was diverted to the outfall, to the marine outfall. So there's no more mercury going into. So the sediment has no mercury at all. And then suddenly, there were hot spots of 1 ppm of mercury, something that it's not allowed anywhere in the world because of dredging for the competitions. So this legacy is everywhere. There's an example, a very good example in Rio Grande, where an old hat factories from 200 years ago used a lot of mercury, and it was there, and then they decided to expand the city and then touch the sediments enriched in contaminants. So wherever you go all over the world, this legality of our responsibilities there. So you have to take care. Agriculture. This is what comes out from a typical fruit agriculture today and what it was without the agriculture, just with natural vegetation. Again, you increase, like phosphorus, for instance, 2 orders of magnitude. So as an ecologist, I cannot see a natural community behaving the same way under 1 ton of phosphorus or 100 tons of phosphorus. So there must be a community which is completely affected by this new situation. We studied soils under irrigated conditions and the natural soils. And along the time, obviously they don't put lead in your lettuce or in your tomato. I mean, it's not on purpose. But any kind of substance you use in agriculture comes from natural sources. A natural source has metal as tracer. Since you do it permanently in the same area, in the end you carry on accumulating those metals. So even a beautiful fruit plantation with beautiful bananas and coconuts and in a very idyllic environment, in fact, is accumulate pollutants through the years. And there's no way of solving this. No way of solving this. Yeah? You can diminish it by changing some practices, reutilizing the organic matter, but no way. Again, and the effect of that in the continental shelf. Well, this is in Ceará State, something very small. I mean, I think Alan already talked about that, about the Mississippi Delta. And then we're not talking about idyllic coconut plantation in Ceará. We're talking about the largest agriculture area in the world, which is the Mississippi Valley. And then the impact is much larger. Yeah? So if you think that an area which is nowadays is about nearly 20,000 square kilometers of, and this was the first one to be identified. Today it's all over the world. Anywhere you have large agricultural basins, you are developing anoxia in the continental shelf adjacent to that. This is everywhere. In Oregon, California, China, anywhere. And what are we going to do with this? I don't know if anyone has a solution. I don't know any solution. You cannot say, well, stop planting corn in the States. Forget about corn. So forget about fuel, forget about meat, forget about everything, because it fuels everything. So to stop this in occurring, you have to make very drastic change in the way humanity treats the planet. And I don't know if there is any solution, at least in the near future. So these things will change and increasing. There is a very nice paper, I don't know if I put it for you. There was some very intelligent people. There are people that has really intelligent. They use large oceanic fish, pelagic fish, to monitor where this low oxygen area are going, because they need a lot of oxygen. So if oxygen decreases just a little bit, they move to a high oxygen area. So if you put a target in that and follow it through satellite, you can analyze where those low oxygen areas are going. If they are increasing, decreasing, moving. I would like to have thought about that. It's fantastic. But even if I did, here it would be impossible. And this thing goes back. It's not only the Mississippi. This is a paper we published from our institute some years ago. We make a budget of the amount of carbon. You know, the people that are not Brazilian doesn't know that USP was in the middle of one of the most beautiful high biodiversity forests in the world, which is the Brazilian Atlantic forest, that cover all that area. You can see on the map over there. It's probably is the tropical forest with the highest biodiversity, and nowadays is reduced to 7% of the original area. So it's like devastating all England, leaving just London with some trees. Yeah? So the amount of carbon that came out for burning these forests, and we plotted it in a graph from 1850s when they start exploring it to the top of the exploration between the early last century, because transforming this in coffee and sugarcane plantation, and the amount of carbon that goes into the river, into the ocean. So this carbon is basic black carbon. It came from burning of tropical forests. Black carbon can last in nature, in the sea, in the ocean, over 1,000 years. So all the carbon that has been emitted by the destruction of the Atlantic forest in Brazil is presently cycling in the ocean. So it's quite possible that even the carbon cycle in the ocean has a very strong anthropogenic component. And well, you know, in that electronic address you can find the full paper. I mean, we have traces of this carbon in the ocean, and it's exactly the same carbon. The black carbon that is in the ocean, in the South Atlantic Ocean, came from the Atlantic forests of Brazil during the 80s, an anthropogenic vector. Another characteristic of the anthropogenic driver is that they are fast. They are very fast, much faster than any governance you think about. There's an evolution of shrimp farming at the Jaguaribe River, where I work, between 2001 and 2006. Nowadays, it's already 4,000 hectares in 2015. So there's no natural process that grows in such speed. Yeah? So the emission of phosphorus, that was about 20 tons per year, from around 8 hectares per year, just 5 years after, increased to 61 tons from 1,600 hectares in 5 years. There's no natural community that can adapt to such an increase in nutrient input in such a short time. No, at all. So obviously, the impact in this environment is huge. And again, when I talked before about the tricky about these processes being the same, they are not, they are the same process, but their speed are completely different. We talk about eutrophication, the first table of the impacts from the major drivers. Nearly all of them provokes eutrophication. But they provoke different eutrophication depending on the origin of the carbon that eventually is the primary driver of eutrophication. If we're talking about agriculture, the carbon produced here that will be eventually supplying nutrients in the coast and creating eutrophication stays in the soil for a long time, degrades in the soil, and is eventually exported to river basins and eventually exported to the coast. Yeah? So when it eventually arrives there is why you don't have anoxia in the Mississippi River process proper. You have the anoxia down in the ocean. Yeah? You have to go all the way from the continent to have a carbon available for being oxidized and liberating the nutrient baggage to produce eutrophication. So it takes a long time to trigger eutrophication when you're talking about carbon from agriculture. If you're talking about carbon from urbanization, well, this carbon came from us. I wonder that maybe in mostly vegetarian countries, this line will be close to the agriculture. It will be basically terrestrial plant carbon. In most Occidental countries, we have a mix of foods, and probably we are in between. Our feces has carbon from both terrestrial and marine origin. Today there was fish meal in the, you ate fish, I ate meat, and this combination makes a kind of carbon which is less or refractory than the carbon from agriculture, so it provokes eutrophication faster. And then you have eutrophication due to shrimp aquaculture, which mostly carbon are from marine origin. Yeah? Other types of agriculture, like tilapia and things, use soya as a major source of protein. Then it's like agriculture carbon, but not shrimp farms. Most of the aqua feeds from shrimp farms are basically fish meal, bycatch, marine, oceanic, therefore marine carbon. And marine carbon are very less refractory than terrestrial carbon. So eutrophication is very fast. So this picture here was taken exactly in 2006, exactly in this area, receiving the effluent from this huge aquaculture that's only that. I'll try. I talk too much anyhow. Well, the other driver that I talked about, which is damming of rivers, the most important thing is that damming of rivers disclose the fluvial flow to rainfall. So it doesn't matter if it rains, the fluvial flow is kept continue, except when there's true floods. Otherwise, therefore, all seasonality in the river and in the estuary, which is based on this, high and low flow disappear. Yeah? And this is the fluxes of the Jaguaribe River after all the damming that started in the beginning of the century, last century, up to today. So it's a river that can easily go to 7,000 cubic meters per second and zero. So imagine the variability, enormous. So all the natural communities evolved in this variability. Now there's about 20 cubic meters per second every year. First result is a huge accumulation of sediments. You can see all the area increasing in sediments and being colonized by mangroves. So as I said, mangroves love this kind of alterations. You see, here's another small river in Ceará where mangroves in less than 30 years more than double its cover. In fact, in the northeast of Brazil, there's about a 25% increase in mangrove area because of that. Mangrove love those things. They're pretty good. Water diversion is a very important problem. And there's again, this is Sepetiba Bay. We work on the management plan of the bay for ages. And this is the amount of material that comes into Sepetiba Bay. This is sediments, basically. So BS is the bay, the basin of the Sepetiba Bay, and Paraíba do Sul River is a river that starts in São Paulo state and crosses from Rio de Janeiro, Minas, and is diverted to Rio de Janeiro to supply water, and from Rio de Janeiro to Sepetiba Bay. So today, more than 70% of all the sediments that goes into Sepetiba Bay and all the water that goes into Sepetiba Bay comes from the Paraíba do Sul River. Meaning that Sepetiba Bay, that was a coastal lagoon with high salinity. Salinity varied between 25 to 35. Nowadays, vary from 0 to 35. Yeah? And most of the material that comes are not produced in the basin. It's producing outside the basin. Not only sediments. Well, there's a sedimentation rate in Sepetiba Bay from the beginning of the century to after the diversion. So it increased, contrary to the, I know, 1 minute. Increased a lot, and then you have a coffee, and I'll have you back. So no problem. I still have 1 hour. And pollutants. Over 60% of all the mercury that goes into Sepetiba Bay in the particulate form, and nearly 50% on the dissolved form, comes from the Paraíba do Sul basin. So we spent maybe 80 years working with the government on a beautiful plan for Sepetiba Bay. But this plan has no governance in the Paraíba do Sul basin, mostly because most of it is in another state. So the Rio de Janeiro plan doesn't work there. So our plan for Sepetiba Bay, you know, it was a very mean exercise. Well, maybe we go later talk about this. since we have only 1 minute, but we need to go back there. Yeah, so I go there. We can have a coffee now, and then I'll have you back. I'll be back.